So the stupidest thing I saw in Hackaday today was somebody making a 3D printer out of Cheese Whiz. So they have a spray can, you know, and the nozzle control with the robot, and it's printing 3D cheese. It's not very accurate.
Wolfson's lab, we talked about, they have that food safe 3D printers.
Yeah.
And they talked about doing frosting cookies and stuff.
I've seen them. That's very impressively silly. But it's, I mean, you could do pictures, you could do arbitrarily complicated things, you could do fractals on your cookies if you wanted. So that's all right. Oh man.
I found out that model sims crashes if you have two model sims open, one of them crashes just after 5 minutes.
So, in fact, there's a QSys. Sophia broke.
You hit run and
it died. So you changed computers and it worked.
Yeah.
Did you try restarting the computer?
Yeah, we tried that.
And didn't fix it.
The license, when we opened it, it said like license needed, like the license file was invalid or something.
So, by the way, folks, there appears to be a memory leak in QSys. If you open up System Monitor and watch the QSys image, it just keeps incrementing memory. And on my machine, when it gets above about 2 gigabytes, it slows way down. And the only solution I've found is close it between generates. Not every time, but every 2 or 3 times. Yeah. Go figure. So, how was lab last night? What artifacts, what messages do you have for people debugging? Anybody? The thing which killed you for 4 hours, then you went, oh crap, and fixed and it worked. There's one I know of, and that is your state machine takes a new value, which is computed combinatorially, shifts it into U, and then U is shifted into U minus 1, and U minus 1 is shifted into U minus 2, and then U new is a function of U minus 1 and U minus 2. That is incorrect. That extra delay of 1 cycle makes the system unconditionally unstable. It produces a very adequate white noise generator. So that's one thing I've seen. You want to, if you're going to do it this way, make this be the new value, get rid of that. That's one thing. Another thing, did anybody have trouble with overflow? Overflowing the number system?
We don't know how we fix it though. So.
Oh, this is where you did some ridiculous mumbo jumbo and it started working.
Yeah.
Yeah. All right.
Well, we did something and then we undid that thing and then it started working.
Now that's not. I mean, there used to be a compiler we used, CodeVision, that had a built-in editor. It had an IDE. But if you imported text from, say, Word into it, you could cut and paste it in, and it looked fine. But CodeVision was susceptible to the non-printing characters that Word puts into a file. Debugging that, you get it. You'd compile it and say, main is not defined. There it is right there, MAIN. You erase it, retype it, it works. That kind of thing just drives you insane. And that can happen, but that's not what this is. It's something else. Although there could have been an embedded control P in there or something, I suppose.
Maybe. Yeah, we're going to try to go line by line between fixed and non-fixed and figure out exactly.
Seems like a good idea.
Yeah.
There's another overflow mechanism which is fairly common. If you go to 1.17 format, you have no extra dynamic range. And so when you form this ui minus 1 j dot 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 minus 4 times uij, there's several ways this can overflow. One, you add up these 4 input leads to the node. If any one of them is greater, if they're all are greater than 1/4, or the average is greater than 1/4, the sum overflows. You multiply uij by 4. If it's greater than 1/4, it overflows. And so the numerically stable way to do this is to go ui minus 1 j minus uij parenthesis plus ui plus 1 j minus uij dot dot dot. So you take the differences before you do the adds, and you make sure the differences are in parentheses so that the arithmetic is forced to happen before the sequential adds. There's also one place where you do a shift to form 2 uij, and so 2 uij. So I would say that you have to be a little careful there about overflow also, but in general, you're going to want to set the initial condition for testing down around 1/8 or 1/16 of full amplitude, and then turn it up. The system does not fail gracefully under overflow. It fails suddenly and noisily. Now, it's not so bad when you're playing it in MATLAB, because at least you have a little warning. You can look at the waveform and see it. But when you put it on the hardware by next week, then you play a fairly low amplitude, so you have the speakers all the way turned up. You increase the amplitude a little bit, it overflows and goes to full power square waves coming out of the speaker. Yeah. What else on? Any other gotchas that you found in the numerical stuff? Everybody got 10 by 10 working? So that's good? Good. Do you want to hear more about the audio codec? Oh, let me see if I can find the link to the Wolfson codec. I think I put that in Lab 2. Nope, Lab 3. Yeah. This is one reason for mentioning this is that this is a chip that's outside of the FPGA, and it is itself a computer with a very complicated state machine, and you have to deal with it. Now, it's the dealing with it is being hidden from you by the abstraction of the audio-visual interface in QSys. But behind the scenes, there's a control interface on this thing, which is I2C, low speed, boring I2C. At the top here, it's got the usual S clock and data, which controls all of the functions. Then there is the high-speed interface down here, which is DAC left-right clock that signals left channel versus right channel, and it is therefore a sample clock. DAC data, which is a serial data stream, and then a bit clock for the data stream. So all of the high-speed data from the audio interface is streamed through this, and there's a FIFO there that buffers it. But you can do all kinds of interesting things with this. For instance, there is right line input, left line input, and a microphone input. You can mix these together. You can mix any of the inputs together, send them through the ADC and out through the audio interface to the FPGA. You can also mix them together on the Wolfson chip through these various bypass channels which do summing here. So you could, if you wanted to, try and make some bizarre karaoke machine where you're singing into the microphone. I see pain on a couple of people's faces. Why did he say that? And so the drill here would be to take music in, strip the voice out of it, put it back out through the DAC, and then have a person sing into the microphone interface. There's a gain stage for the microphone, 20 dB gain stage built in. There are volume controls for the inputs. There are mutes for each of the inputs. There's volume controls for the outputs. There's a 24-bit DAC for left and right channel, plus mutes at the output. There's a lot of stuff you can mess with. You can set this all up through the AV config module. But it's a very cute separate processor. If you try to violate Nyquist criterion, let's say that you're going along plugging out samples that are all 0 through that serial interface, and you give it a full amplitude square wave, the built-in digital filtering here will make sure that the system rises smoothly between samples so that your square wave becomes degraded enough to satisfy, what is it, sine x over x. It satisfies the Nyquist interpolation. That's cool. So it's very cute. Occasionally it will hang. It happened more on the DE2 than on other boards, but it seems like it does occasionally hang. If it hangs, you can try and restart, but probably you'll have to cycle the power. Which means bringing down Linux first. So, what do you want to hear about here? Want to talk more about parallelization? What's on your minds at this point? Yes?
Can you give a rough order of magnitude approximation of how long or how fast the bus interconnects are within that FPGA?
So the question is, can I estimate the bus speeds within the FPGA? And I think I can. I'm not sure I have it all right because I haven't tried the streaming interface, which I believe is faster. But if you go for the so-called MM interface, the memory interface, it looks like the HPS side through the heavyweight bus to VGA is about right around 5 million transactions, 5 to 10 million transactions a second. So you can get about 10 million 32-bit words across that per second. That's fairly low compared to the speed of the HPS. So if you are putting out lots of stuff across the bus, you're going to slow down the HPS, if that's the only thread running. So if you are on the Avalon side and not going across the AXI bridge, I think that the speed is about 10 times better. I think it's on the order of 50 million per second. It's plenty fast enough for the audio interface and for doing copying fairly big buffers. Is that yeah. What else? Do you want me to go over the audio state machine again? The bus master state machine? Again, that's fairly straightforward. I would say that the best state machine to look at is probably in the DSP page. You might want to look at audio loopback or audio filtering, where I'm actually using the FPGA to do some sort of digital filtering. Again, you're not going to be using loopback because you're not going to be taking any input from the audio interface. You're going to be strictly doing output from the audio interface. You want to see this again or no? No? Yes? Yeah. So again, the QSys design. This is a fairly small QSys design. There's nothing but the ARM, the AV config, the audio subsystem, and bus master. So the bus master here, the interface, is driving the audio subsystem slave, and that is now the audio output. So this connection is going to carry all of the memory transactions necessary to manipulate the interface, including reading the FIFO and writing the samples that you want to output. The connection to the bus master audio external over here is, of course, what you're going to then wire up in the top level module. So this version is somewhere, is of course defining all the addresses, and I hooked the red LEDs to the FIFO space, not because I can see lights flickering at 50 kilohertz, but I figured at least I could see the high watermark of how full did the FIFO get before my state machine loaded it, and the fact is it never got more than a couple of samples in it. I generated two possible signals for the left audio output, which were either the output of the direct digital synthesis shifted by 16 bits. Why 16 bits? It's because my DDS was 16 bits, but I left the audio interface at 32-bit resolution, so I had to shift everything over to scale it to maximum amplitude. You can set up the system to be 16-bit or 32-bit data. I suggest 16, since it matches very well with what you're doing with the drum. But that's up to you. But in any case, if you use the 32-bit interface and you output 16-bit data, it's going to be very, very quiet. All right, you won't hear it at all. It'll be 90 dBs down. The next block here just does the direct digital synthesis and it's waiting for audio input ready before it generates the next sample, that locks it to the audio input. You are probably not going to do that. You would probably lock it to the audio, your synthesis to the audio output state machine. And then my input here just built a sine wave running at 375 hertz. If you can't figure out what's going on, hook some of these bus control signals to GPIO pins so you can watch them on the scope. You could put a state 0 flag, a state 1 flag, a bus read, bus write on there. You can watch your states fly by on the GPIO pins, and make sure that the read and write signals, well, you're not going to have a read signal. Make sure the write signal occurs during the right state of your state machine. Then the main piece of this is that you're going to read the FIFO. Geez, that's horrible. Let me see. Read FIFO, write data if there is room. So we put the audio FIFO address on the bus. We set up read. We wait till the ACK is true. When the ACK is true, we know that the data bus is valid for at least one cycle. Read it fast, folks. And so we read the bus data. We shift it by 24 because that happens to be the data format for the left channel. And then, if there is FIFO space, I'll put the left data. Set it up to the data left address, do a write, and if there is no space, just wait a while. Wait a few cycles, try again. If the left channel has space, the right channel has to have space because they increment at the same rate. So after the bus terminates, after the write terminates, you do the right channel write, detect the bus end, and then what you're going to do at this point is you're going to loop, after you do the check for the bus clear at the end of the second write, the right channel write, you're going to go back up to state 0. I would also throw a flag here, set a flag bit saying, do a new calculation. Because given that you've just done a write, you have 20 microseconds before you need to do another write. So any questions on this? It's really straightforward. This shouldn't be the rate limiting step, I think, for this lab. But getting the details right is always. Any question? You have. I wasn't sure whether that was a question finger coming up or. Well, yeah. So, a completely different alternative for doing this lab is doing floating point. Or maybe do the Mandelbrot set in floating point. Complex floating point. Ooh. And so I've been working on getting the floating point cleaned up a little bit. Thought I'd talk about that just a little bit here. I'm on. So, wrote a new page called Floating Point Hardware. And this is based on the work of 3 students, primarily Skylar Schneider, who came up with a system, and then Mark Eiting, who modified it for slightly better performance for the operation 1 over square root x. The reason being that Mark Eiting wanted to calculate gravity, which goes as the reciprocal 3/2 power of the radius vector. So the scheme that Skylar invented that Mark modified is the following. It's 18-bit mantissa. So it really shouldn't be called a mantissa because it's not a logarithm. It should be called a significand, but everybody calls it mantissa. So it's an 18-bit mantissa, 8-bit exponent. So it has a range of 2 to the 256. Divide that by 3.2, and you get a range of something like 10 to the 60th or so. I believe it's actually 10 to the 72. So it goes from plus 10 to the, from 10 to the 38th to 10 to the minus 38th is the magnitude range, more or less. 8-bit exponent and a sign bit. The format is 2's complement, is not 2's complement. It is sign magnitude. So this is a positive magnitude. The exponent is in slightly odd units, where 2 to the 0 is equal to 127 in the, let's say 2 to the 0 maps to 127 value in the exponent, and the sign bit is 0 if the number is positive. 0 implies positive. And it's packed into a 27-bit word, which is given up here. It's packed into bit 26 being the sign, 25 through 18 the exponent, and the fraction is 17 down to 0. So 18 bits. Anybody know what IEEE 754 is? That's whatever you all use all the time. Is standard floating point. That's what every CPU you've ever used is programmed with. How many bits of significand? Anybody know? Oh dear, how do you know when you're making a mistake? You assume it's perfect, in fact, right? But it's 24-bit. 24-bit. It also, I believe, uses an 8-bit exponent and a 1-bit sign bit. So IEEE standard is 24-bit, 8-bit, 1 sign bit, and fits in a 32-bit word. What's wrong with that picture? Where they put the extra bit? Well, it turns out that the way they do it is that the significand is stored as a normalized number. That means that the high bit, which represents the ones place, is always 1. It's normalized. If the high bit is not 1, you shift the significand until it is 1. If it's always 1, you don't need to store it. And so there's an implied bit here. It's 24-bit, but you only store 23 because you always know the higher order bit. Mark did the same thing. He's storing actually 19 bits, but because the multipliers are 18 bits on this architecture, he actually right shifts it before he does any arithmetic and reduces the actual resolution to 18 bits. How good is 18? What do you need for video? Let's say you're building an MPEG or an MP3 encoder. How many bits do you actually need to carry? Turns out there's a bunch of research that's been done, and the answer is 9 or 10 bits. Not much. How much you need for doing DSP? Well, for audio. Well, that depends on exactly how accurate the audio is, and it depends on how you build the filter. Some filters are more stable than others. FIRs are sort of unconditionally stable. IIRs can be unstable, but if you factor them into second order sections, they become pretty stable, numerically stable, but typically 16 bits would be enough. So 18 bits is not bad in terms of signal processing for human I/O. It's horrible if you're building, say, atom bombs, or doing high precision calculations like weather predictions that are highly iterative over a long period of time. But it's not bad. This is, by the way, the next size up for the multiplier. The multiplier will do a 20, each DSP, what do they call them now? Multi-resolution DSPs will either do 2 18-bit multiplies or 1 27-bit multiply. So if somebody wanted to change this system over to 27-bit, 27-bit mantissa, that would work pretty well in this architecture and would give you even better accuracy than IEEE. Except you're probably not supporting rounding, which IEEE does. IEEE supports a whole bunch of special cases. It rounds properly. It knows about underflow. It knows about negative infinity, positive infinity, and nan, not a number. And Mark and Skylar's system knows none of that stuff. It's stripped down for being small implementation rather than have lots of special cases that enable numerical stability. Any questions on this? Yeah.
What's the 2 to the power of exp minus 1.7?
So this is the value of what you're outputting. So when you store, let's say you store the number 25, you're storing it as 131 minus 127. I mean, that's the value of it, is 121 minus 137. What you're actually storing is 131.
Okay. Oh, okay. That's why 2 to 0 is 1.7.
Maps to 127. Yes, exactly. Yeah.
Okay.
So we can ask, what is the representation of 1.0? And it is 1 FC 0, 0, 0, 0. Now look, that's it. Wait a minute, that looks like a negative. No, it turns out that because this is a power of 2, 1.0000, if we look at this is the binary now. If we look at the binary, only the high order bit is set, the rest are zeros. So you have 16 zeros here, plus 2 more because the low 2 bits of the C is 0, it being 12. 2 bits, 4 bits, 1 bit is 7 bits of 1, which is 127. And then the sign bit is 1 because it's positive, otherwise there would have been a 1 out here if it was negative.
Wait, the one out there, or would have been a 2 out front?
It would have been a 3. I'm sorry, yes, it would have been a 3 there, yeah. Sorry. So it's fairly compact, fits nicely into the architecture, and it's fairly small. A multiply is actually smaller than an add in terms of logic units, but uses 1 DSP module. Actually uses 1/2 a DSP module. To test this, I decided to, rather than reprogram the FPGA a bazillion times to test all this stuff, I made a interface to the HPS. So there's 3 bus slaves, just like you did in Lab 2. There's 3 bus slaves, argument 1, argument 0, and result, that are feeding back, are getting data from the HPS, then feeding back a result. And I put a clock bridge in here to do a clock adjustment, because at one point I thought I was having a race condition when in fact it was just stupidity on my part. And so what I've implemented so far are the 3 things that Mark had, plus a couple of others. Floating point add, and I modified the floating point add because I think the underflow flag was wrong. I think that he was doing underflow incorrectly, because there's a case, multiplies are easy. You multiply 2 normalized numbers together, numbers that are between 0.5 and 0, and you're going to get a number that is between 0.25 and 1. If it's less than 0.5, you have to shift it one place to renormalize it. Done. So given that you could do a multiply, doing the renormalization is easy. If you add 2 numbers, your 2 numbers that are normalized, so 2 numbers that are normalized, you have to make sure that the exponents are the same, but they're both going to be between 0.5 and 1. And 1. And so you have, so the sum is going to be between 0.5 and 2, which may mean you have to shift 1 to the left or 1 to the right to renormalize. But where it really kills you is if you have something like 1 minus 1.0001. Now you get cancellation of all the high order bits. And all of the information is going to be carried way out here to the right of in the significand, and you have to shift it way over. And when you say shift way over, it means hardware. So there's a big multiplexer that has to be built to make an add run correctly at 18 bits. And the flag that Mark produced to show that an underflow occurred, let's say an underflow would happen if you said 1 minus 0.000001. The system holds about 5 places of accuracy, 1, 2, 3, 4, 5, 6. If you give it 6 places of accuracy, this evaluates to 0. That's an underflow. But his was giving an underflow with 10 minus 10.1. Oh dear. So This is only 1 part in 100 difference, and it was already saying it was 1 part in a million difference. So it was wrong. I think I fixed it. It's hard to get all the edge cases right. I'm doing static tests right now. After I get this done, I'm going to have the HPS generate 10 trillion numbers and feed them all through the thing and look for errors, let it run all weekend. But I haven't done that yet. So I think I fixed the underflow problem. Second is full floating point multiply. Oh, yeah, the add is a 2-cycle pipe. Because of the big multiplexers, it's slow. Floating point multiply is combinatorial. It's fast, it's easy. Floating point inverse square root is 5-cycle pipeline. And one more multiply converts inverse square root to square root, obviously. Multiply by x over square root of x gives square root of x. So inverse square root gives you square root also. Floating point negate, he didn't write. That's really trivial. You write a module that flips the high order bit. And one thing that's always bothered me is that there's no floating point shift operator. So I wrote one. It's really easy, but nobody does it for reasons I'm not entirely sure of. Because all you have to do a floating point left shift is to increment or decrement the exponent. You just ignore the rest of the number, ignore the significand, and just change the exponent by 1. You've multiplied by 2. You increase the exponent by 1, you multiply by 2. So this is floating shift. I haven't gotten to floating point end and into floating point yet. That's actually fairly annoying. So I got to work on that. My goal is to have a set of floating point routines that you can use routinely if you prefer it to fixed point. It's going to be slower than fixed point. It's going to be bigger, but it does ease a little bit of the load on your brain, and that's something to be considered too. So, what's your favorite operator would you like to see? Yes?
Oh, wait. Okay, you can define floating point modulo, I think.
Ooh, floating point modulo. So let's see.
I had to use it once I remember. I think it's defined somehow. Which, it doesn't make sense. It has to have integer
It doesn't.
on the right side.
Yeah, it doesn't make sense unless it's integer right side.
Yeah.
At least. By the way, the first time I had the little test input on the HPS. You input 2 floating point numbers. You hit return. It gives you the answer back. And there's some switches you can set to which output you want. First time I did it, the floating point shift gave me back exactly the input. So I screwed around with the hardware a little bit. That must be a bug. Try it again. It gives me exactly the input. What the hell's going on? So I was using fairly round numbers like 1, 2, minus 1, minus 2 because those are shifts that make sense. The low order bits are always 0, and I was feeding it a floating point number. So it was taking 7 bits, which was those 2 digits, and giving me exactly 0 shifts, which was the input. So this takes as input right now a float for the number to be shifted and an integer for the number of shifts that has to happen. That suggests that a floating point, integer to floating point, is going to be necessary for this to be completely general. Nobody's going to say divide? Or you could just square the floating point inverse. That's crude. It might actually be, that's a very optimized routine. There's this, do you know this graphics floating point thing? this graphics floating point fast inverse. Let me see if I can find it. Fast inverse square root. XKCD, let's see what XKCD has to say about that. Oh, no, that's too hard. Okay. So there's one of the you do this really odd thing to get the norm of a vector, which is used a lot. You take the input, you shift it by 1, you subtract it from what? What? And then you do this? Well, that's a Newton iteration. Some of you remember Newton iteration. You're finding the zero of a function. That's finding the zero of a function. What in the hell is that? Well, it turns out it uses a trick of the format of a floating point number. A right shift, after all, divides the exponent by 2. That's a reasonable approximation of the square root, right? Dividing the exponent by 2. It only works for positive numbers, so the higher order bit better be 0. So you divide the exponent by 2, and it turns out that half of the, and then you mask it, and a fraction of the mantissa is a reasonable approximation of the significand of the square root after you do the masking. How is this derived? I have no idea. That's too weird a number to have just been pulled out of your nose. So somebody had an idea someplace about that. And then you do a standard Newton iteration if you want to do it. That gives you 0.1%. If you want to do it twice, you get as much as you need. So that's what Mark implemented, and why he had to change the format so that it was the same, so that the format was homologous to IEEE format, so that the fast floating point would work. So the first hack at the top level module just defines floating point shift, floating point sign negation, and then this strange square root. But Mark's and there's the bizarre stage 1 constant modified for 18-bit rather than 24-bit, and got it all working so that they could calculate. They could calculate. See how slow this is to load up.
Hi, my name's Brian.
Yeah, sure it is. Okay, so this is the gravity simulator running.
So you have 20 accelerators, and so you can calculate the force on 20 particles at the same time, or from 20 particles.
The idea is we load up 20 particles into the engines, and then we run every other particle by those 20. So then we have the net acceleration, which we can then use to calculate a new velocity and position.
Necessarily conserve energy, but it's good enough.
So
It's impressively fast.
So a slight modification of this video, for some reason or another I have yet to figure out, made the trending list top 50 videos on YouTube for 2 days in January. And the video quality, this was the good one, the video quality was so atrocious on it due to my camera work. The trolls went crazy and kept it in the top 50 for 2 days, for 50 hours. It got 50,000 views in 2 days. The power of the internet. for good and for bad. So, so as it stands now, there's a working add, a working multiply. That is enough to actually do Mandelbrot set. Oh, you need a compare also. Oh, I need to write a floating compare. Forgot about that. Floating less than, floating greater than, yeah. Floating equal, whatever that means. So I will do that. Any questions on this? Part of the reason for me writing it initially was I did a 9-bit version, because until you actually write something like that, you can't possibly teach it. You say, I don't really understand it until I can make it. That's a modified quote from Richard Feynman. But I don't mind stealing from Feynman. All right, I'll be in lab this afternoon. If you have any questions, I have got a couple of people coming in for meetings, but I'll be around all afternoon in lab.